We're going to see how we can use Newton's laws to analyze a situation where we have two objects moving together. In this case, we have two blocks, a 12-kilogram block and an 8-kilogram block attached by a rigid cord. And rigid just means that it can't stretch. And they're both being pulled by a 50 Newton force accelerating to the right. And we want to find out the acceleration of each block, the tension in the connecting cable, and then we also want to do this with and without friction and see what's different about them. So to get started, when we ask for the acceleration of each block, because they're attached by a rigid cable, that means we can assume that the acceleration of the red block is equal to the acceleration of the blue block, because they are attached by a rigid cable and they have to move together. The cable can't stretch. Now we're going to use our same techniques. We're going to draw free body diagrams, write Newton's second law equations, and then use them with equations like our gravity equation and our friction equation to solve this. But there's one trick when we have multiple objects. When they're moving together, it's often useful to draw a free body diagram and analyze them as if they're a single object as well. And it's going to just make our life a little bit easier finding certain things. So the first step we're going to do is I'm going to call this whole thing, the two blocks together moving, as one system, and analyze them as if they were one object. Kind of like if you're analyzing you sliding, playing baseball or playing soccer or something like that, you wouldn't analyze every little bone of your body separately. You would analyze your whole body as one system and how you're sliding and how you're accelerating. We can do that as well for this. Now, if I wanted to figure out the interaction forces between your bones, I need to analyze each bone independently. So we're going to do that. We're going to analyze our system as one big system and then analyze our objects independently and use them together to find out what we're looking for. So let's first make a free body diagram of our whole system. Now we're going to start without friction, then we'll add friction afterwards. So for our whole system, we just have a normal force due to the ground. And I'm going to put a T after these to remind myself that these are for the whole total system. We have a gravity force. And then we have our applied force of 50 newtons directed to the right. And that's it. Because we're analyzing the whole system, that internal tension, that connective thing, it doesn't show up in this free body diagram. It's not outside our system. It's not from another object acting on our system. I'm also going to quickly calculate the weight of our object. So remember, this is the total weight. So this is going to be the total mass, which is 12 plus 8 kilograms times our gravity constant, which we're going to use 10 newtons per kilogram, assuming that this is happening on Earth. So that is a total weight of our whole system of 200 newtons. Now let's write some some Newton's second law equations. So in the x direction, we have just our applied force, and that is causing our total mass to accelerate. And in the y direction, we have our normal force minus our gravity force, and that is causing our mass to accelerate in the y direction. Now these are sliding along the ground, so we can assume our y acceleration is 0, which means our normal force equals our gravity force. You might be getting sick of seeing this again and again, but remember, this is not always true, so it's always good to write it out, especially when you're doing homework problems and stuff, when you have the time to, just so you don't get the one time you do skip over this and assume they're equal to each other, you don't get tricked, and that's the time that they're not equal to each other. But in this case, they're equal to each other, and that is 200 newtons. And now if we jump to our x equation, we have our 50 newton applied force. So that's going to equal our total mass of 20 kilograms times the acceleration we're looking for. So we can easily solve this. The acceleration of the whole system is going to be 2.5 meters per second per second. Now, if we want to find that interaction force, we can look at I'm going to choose the red object here, just the red object by itself. So I'm going to draw a new free body diagram of just the red object. So we have a normal force acting on it, but this time it's on the red object, not the total. We have the weight of the red object, which I'll do this really quick while we're here. So that's going to be 12 kilograms times the same gravity field constant for 120 newtons of weight. And then now, this applied force is not acting on the red object. It's acting only on the blue object, so it will not show up in the red object 3x diagram. The only other thing acting on the red object is this cable that's connecting them. So I'll throw in that, and I'm just going to call it T for now. And that's the tension we're looking for in this connective cable. So there's my 3x diagram. I can write two Newton's second law equations for this. So we got the sum of the forces in the x direction for the red object is going to be now the tension force. That's going to equal the red object's mass times the acceleration in the x. And then we can do the same thing in the y direction. The normal force in the red object minus the weight of the red object equals m times a. In the y, again, no y acceleration for the red object. So the normal force on the red object is equal to its weight, which in this case was 120 newtons. And then we can use our x equation for the red object to solve for the tension, because the red object has the same acceleration as the blue, and it has the same acceleration as our total acceleration. So this acceleration here is the same as that acceleration. So we can use it to solve for this tension force. That's just going to be the red object's mass of 12 times our acceleration of 2.5 meters per second, which gives us a tension of 30 newtons. So again, we looked at the system as a whole, analyzed it, looked at just one of the objects, analyzed it, and used those results together to figure out the acceleration was 2.5 meters per second, and the connecting tension was 30 newtons. It's also nice to notice here that the applied force was 50, but the force acting on the red object was only 30. It was less than the applied force. All right, now let's add friction. So by adding friction, we're going to add some extra forces. So we have to change our free body diagrams. So we'll go back to, again, we're going to use the same steps. We're going to start with the object, with both objects as one big system, and then look at the red object and solve for a new acceleration and for a new tension force. So in our system, we have a friction force added. It's moving to the right. So friction is going to act to the left. Force of friction up. Again, I'll put a little T to remind me that it's a total force. And I'm going to update my red object's free body diagram. We have a friction force here acting on the red object. Now we only added a force in the x direction, so our y equations, you don't have to change at all. They're going to stay the same. We will have to update our x equations though. So let's go back up here. I'm going to keep the m times a part. We're going to have a new acceleration. Just remember the old one was 2.5, so we can compare it. And I'm going to actually keep the y. Actually, let's just write a note over here that the original, so don't forget little star. So acceleration 1 was 2.5 meters per second. And tension 1 was 30 newtons. So we'll go back, erase this, and we're just going to write two new equations. Let's erase that too. Because we have a new free body diagram. So for our whole object, we have the applied force minus our friction force. That equals m times a. And for our red equation, we have the tension minus the red object's friction force equals m times a. So before we can solve this, we just have to find our new friction forces. Shouldn't be too bad to do. So the friction force total is going to be the coefficient of friction times the normal force. We already know the normal force, so this is going to be 0.2 times 200, gives us a friction force of 40 newtons. We go back into our x equation again. So we have our applied force of 50 minus our new friction force of 40. That equals our total mass, which is still 20 times the acceleration. And that gives us a new acceleration of 0.5 meters per second, which is less than it was before, which makes sense. We added a friction force with the same applied force. Our net force is going to be less, so our acceleration should be less. So that shouldn't be too surprising. Now let's jump down to our red object to find our new tension force in the cable. So we have to find the red object's friction force first. That's going to be the coefficient times the red object's normal force. So that's going to be 0.2 times 120. That gives us 240, or 24 rather, newtons of friction force. And then we can plug that back into our red object equation. So our tension minus 24 equals our red object's mass, which is 12, times our acceleration. Now, again, just like before, our acceleration of the whole system is the same as our red object's acceleration. And we get our tension force. Oops. Let's be consistent and use our green. Our tension force is going to be, let's see, 12 times a half plus 24, and we bring the 24 to the other side, and we get a tension force of, look at this, 30 again. So that's a kind of unique result. It's showing us that this interactive tension force doesn't depend on there being friction or not. If there is friction, that force stays exactly the same if there's friction or not friction. Our acceleration was different, but that in-between force was the same. Now that might be surprising, but if we think about it, the tension force is overcoming friction, so it should be bigger, but the object's also accelerating less, so you wouldn't need as much force to accelerate the red object. So even though there is friction now, there's more friction, but there's also less acceleration. They balance each other out, and you get the exact same interaction force between the two objects. Now I'm going to show you one more trick, kind of why we can do this system thing, why it works. You don't always have to do it that way. You could actually not use the trick of treating the object as a system, and you'll get the exact same result. So I'm just going to do part of this one more time, but this time not treat the two objects as one big system. We're going to see if we do another little trick, we get the exact same answer. I'm not going to solve the whole problem, just show you how one little piece comes out of it. So let's clear this. So this time I'm going to draw just two free body diagrams, one for the red object, one for the blue object. So we have a normal force on the red, we got a gravity force on the red, and we have the tension again to the right. On the blue object, which we haven't drawn yet, we got a normal force on the blue object, we have a gravity force on the blue object, we have our applied force of 50 newtons, and we have the same tension force just in the opposite direction, because the tension force in the blue object and the tension force in the red object, they're Newton's third law forces. They're equal and opposite forces. They're how the red object and blue object are interacting with each other. So we have the exact same tension, just acting in the opposite direction. Now, I'm not going to look at the y direction right now. Let's just look at the x direction so I can show you how one of our tricks ended up working out. So in the x direction, we have, for the red object, we have the sum of the forces in the x, just the tension, and that's equal to the mass of the red object times the acceleration. For the blue object, we got the applied force minus the tension force equals the mass of the blue object times the acceleration. Again, remember we said the two accelerations are the same. That is still true. So we have two equations. Now what I'm going to do is, their equations, I'm going to add the two equations to each other. So I'm going to add the red equation to the blue equation. So I'm just going to add tension equals, actually let's write it in red so we remember where it's come from. I'm going to add tension equals mass of the red times the acceleration. Now again, because these are their equations, I can add them to each other, and the left side is still equal to the right side. That equation is still true if I add them together. And if I add them, I get the applied force minus the tension force plus the tension force equals mb times A plus mr times A. And now if I kind of clean this up a little bit, I have a negative tension and a positive tension. Well, they cancel each other out. I get just an applied force, and that equals, if I pull the acceleration out of here, mb plus mr times the acceleration. And really what this is, there's our applied force. This is our total mass. So we have our applied force equals our total mass times our acceleration. Well, that was our the equation we got when we treated the whole object as a system. So really treating the whole object as a system is just a shortcut of doing these two free body diagrams by themselves, writing their equations by themselves, and adding the two equations together. Equations afterwards